Okay, so today we're going to be looking at doing some modelling questions, particularly for exponential functions. Now, you guys should all have your cheat sheets next to you that say exponential functions on the top, and then it's got a couple of different pieces of information. It's got a little bit of stuff about how to differentiate, how to sketch, how to solve, all solid gold. So, when we're doing modelling questions for exponential or logarithmic functions, a lot of the time we're dealing with initial values. Now, this is more of a trick about language than it is about you guys knowing anything about exponentials. So, first thing we're going to do is pull apart the language. The number of bacteria on a culture plate, N, can be defined by this rule, where T is the time in seconds the culture has been growing. So, if I substitute in a value here for T, it should tell me when time is this many seconds, how many cultures are present or how many of that bacteria is present. So it's at that time, this is how many we have. Now that is different to if we have a rate. Remember, a rate is another way of saying gradient. Rate is a fancy way of saying gradient. Now, gradient is a fancy way of saying calculate the derivative. Okay, so first thing we're going to highlight here, how many bacteria were initially present? Now, initial is something that screws people quite frequently. When I'm thinking about an initial value, initial is always when T is equal to 0. Okay, and I want you to think about it like this. If I was going to graph something and I had a value here, that would be when X is 0. This is when X is 1. This is when X is 2. Now, if I'm graphing my home loan, and this is the dollars that I spend with respect to time, in my first year, pretend that's a 1, in my first year of owning a house, time is 0. Okay, and that's because when I first buy my house and I move in, I would say that this is my first year of living here. I wouldn't say this is my 0 year of living here. Now, on the graph, though, when I say the first year, that is when time is 0, because if I was graphing it, that's when I first moved in. Time starts from 0 when I first move in, and then after half a year, I've lived here for half a year, so then it becomes 0.5. Yes? So you could also say I'm halfway through my first year. That works. But initial is always when T is 0. Now, that is something that's going to apply in all of your modelling questions. So remember that fact. Commit it to memory. One thing that might help you to commit it to memory is to remember it with this joke. Why was the math book sad? It had a lot of problems. Yeah. All right, so how many bacteria were initially present? Now, the next thing that I've got to decide is what kind of function am I substituting it into? Now, I want to find the number of bacteria that are present. So that means that when time is 0, what is the number of bacteria present? So I want to substitute it back into our normal equation. So N, now to show that I'm substituting in 0 as T, instead of writing the T here, I'm going to substitute in the 0. Now that says to me, I am putting whatever this is here is going to go over here. So 2000, 1, 2, e to the power of 0.3 times 0. Okay, so initially there are 2000. Now 0.3 times 0 makes 0. E to the power of 0 is always 1, which means that I've got 2,000 bacteria present initially. Now, your textbook does something confusing occasionally. They'll tell you that the value in front of E here is always the initial value. And that's a true statement for an equation that looks like this, but not always. So we would say that this is y equals AEKT. Now, you'll notice here that we're missing something important off the end, and that is our asymptote. So if you have an asymptotal value, when you substitute in 0, you won't just get that A value at the front here. It'll be offset by the asymptote as well. So just keep that in mind for later on. Okay, so initially there are 2,000 bacteria present. So therefore, the initial amount of bacteria, which is NO, is 2,000, and that's it. Now, you are going to be writing a sentence for all of these because your problem with modelling questions isn't really the question. It's not even generally the math. Your problem with modelling questions is that you don't know what you're finding. So you don't read the question fully, you don't understand what the words mean, and so you don't know what you're doing. Okay, next one. How many bacteria to the nearest whole number are present after 10 seconds? So, how many bacteria after 10 seconds? Now, the easiest thing to pull out straight away is that T is going to be equal to 10. If I'm looking for the number of bacteria, how many bacteria, that means that I am still substituting into NT. So I want to find the number of bacteria at 10 seconds. So it hasn't asked me for a rate. It hasn't asked me for when, I don't know, how quickly it's accelerating. It's asking me for the number of bacteria. So I put it into the function that gives me the number of bacteria. So N of 10 is equal to 2,000 times E 0.3 times 10. Now, as an exact value, it's going to be this. But this has asked me to get it to 2 decimal places. To a whole number. So I'm going to put it in my calculator. Now, your Euler button is just above here. E to the power of 3, execute. So 40171 point, and we're going to round that to be 0 so that it's a whole number. So 40171. Therefore, there are 40,171 bacteria present when T equals 10. So if I'm graphing this, it's over here. There's my 10. We're looking for this number that comes off in this direction. Okay, still on my regular how many bacteria graph, not talking about the gradient yet. Okay, so next one. Now, I'm going to rub out that little graph so that we can see what's going on. After this, I'll go through the calculator how you could have done this with G-solve the whole way through. Okay, at what rate is the bacteria population increasing after 10 seconds? At what rate is it increasing after 10 seconds? So, we're asked for a rate. A rate is a fancy way of saying gradient, which now means we're still looking at 10 seconds, but now we want to find the gradient at 10 seconds is equal to what? So my first step is to calculate the derivative of this function. So to calculate the derivative of our function, which is what this statement means, I need to derive our initial statement with respect to T. That's how you standardly state that. So if I want to put the original expression in, I state this first, 0.3 T. Okay, now if you look at your differentiation rules that are on the exponential sheet, you'll see that there's similar examples for these. You just have to follow the steps. So our derivative function is given by, we'll take the derivative of this and it will come to the front. So 0.3t, when I derive that, will become, not 2,000, don't get tricked there, times 0.3, bracket, e to the power of 0.3t. Because it's an exponential function, it doesn't change. So 0.3 times that gives me 600. So 600 e 0.3t. So that is a function for the gradient or a function for the rate of bacteria present at any time. So the rate of bacteria increasing, or it could be decreasing, the rate of bacteria increasing at any point in time is given by that. Okay, so next thing that I want to do, I'm just going to substitute into our original function. So when I put in the number 10, it's changed the function to give it to us as this is what it's going to be. So, not that one. So our gradient function, and we're going to substitute 10 in. So 600 times e to the power of 0.3 times 10. 600 times shift e to the power of, oh, well, we know that's going to simplify to 3. There you go. So the rate of increase is 12,051 at that time. So at 10 seconds, the bacteria is increasing by 12,051 bacteria per second. Okay, so if you're thinking about what this rate actually represents, we know that rate of change is when you take two different points and then you average them out. So it's saying to you here that for every 12,051 bacteria, it's going to take 1 second for that increase to occur. Okay, so next thing we're going to do is we're going to look at how we could have performed this whole thing with tech active. So I'm not even going to write anything over here. We're just going to chuck it straight in. Now, I could do it in my regular run matrix, but I'm just going to choose to graph it. So over here, I'm going to graph my initial function. Shift E. And I'm going to draw him. And you'll see that it didn't come up straight away. So I'm going to go zoom and then auto and see if that gets me some information that I want. And that's looking pretty good. Now, the next thing that I'm going to do is how many bacteria were present initially. So I'm going to GSolve for the y-intercept. So when x is 0, y is 2,000. Next thing that we're going to solve for, how many bacteria to the nearest were present after 10 seconds? So if we want to know, input the x, that means we're calculating y. So when x is 10, y is 40,171. So that matches the answer that we got down here. Now, the next thing that we're going to do, potentially I'll show you this in two ways if this first way works. We want to go shift, setup, turn our derivative on here. So mine's already on. Exit, draw. Now we're going to sketch the tangent, and we want the tangent at 10 seconds. So you'll see there at 10 seconds, it's 12,051. So the gradient is that. Okay, which matches what we have. Your other option for calculating part C is if I go math, derivative, I'm going to put in my original function. And go across and enter in the value that I want to solve for. So it's saying calculate the derivative of this function and then input 10. And then we get the same answer again. So there's multiple ways that you can use your calculator to solve these things.